Well, thank you for having me tonight to talk about the Kansas City water treatment plant. As you'll see behind me, this is basically the city's one and only water treatment plant for the entire Kansas City metro area. It was first, we'll start off, Kansas City first started treating water in 1874 over on the Kansas side, over at Klender. In 1926, they started construction at the present location with intake, the water treatment plant, which was designed for 110 million gallons a day. That facility, after several years of continued growth of Kansas City, ended up being too small, so they started to increase the design. So it was designed for 210, and then back, I believe in the 1990s, it was expanded with some additional construction up to 240 million gallons a day, which is what we're permitted to produce. Kansas City has reached a peak capacity of 207 million gallons a day, but that was in 2007 when it was nice and dry and before the economic problems that occurred in the United States. Our average daily demand this year, or actually, excuse me, last year, was 103. This year, since it's been a very wet summer, I don't even know if we're going to break 100 million for the average of this year. A little bit about the water treatment plant. We are 24-hour operations. We have staff that's there 24 hours a day, plant operators that are there to keep an eye on the water, make treatment changes, make pumping changes for our systems to make sure that there's proper pressure for our for our customers to obtain water. We have one intake at the water treatment plant, and there are 14 wells that we use to help maintain water temperature in the wintertime. We try to, with the wells, we try to provide the system with at least 40 degree temperature that helps out with treatment and decrease our main breaks. There, essentially, with this water treatment plant, we have 6 individual water treatment trains, which allows us to, if we need to, test out some new chemicals or test out a new treatment process. We can utilize one train to study it while utilizing the other 5 trains to provide water to the citizens. Recently, we've upgraded our filters. They used to be a multimedia, where it was gravel, sand, but now with the technologies that has come about with sand filtration, we've basically gone to a mono filter. Basically, we have all sand, but there's a box underneath it that supports the media, and it helps improve our water quality. The picture you see behind me is the existing water intake. This was built in 1955. This was actually constructed after the because of the 1950 flood. The brick building was the old intake and low lift, but this was the 1993 flood that occurred, and you're showing the old intake and the old low lift from the 93 flood. As you can see, the old intake was basically out of commission. One of the problems that we have in the wintertime is ice. Something else that's been going on is, which you probably have heard about or read in the newspaper, is river degradation. The river has degraded over the past 50 years 10 feet. What that means is the activities on the Missouri River, whether it's dredging or the dikes that have been put in place or the vegetation that has occurred along the Missouri River, has basically channelized the Missouri River, and it is causing the flows to take the material that would normally sit at the bottom and move it further downstream. The Corps is, along with some of the stakeholders here in the Kansas City stretch, are working with the Corps to try to figure out how to decrease the degradation. What you see in the picture are some auxiliary pumps that we have to stick out in front of our intake during the wintertime when there's low flow conditions. And that's an extra cost that is incurred because we have to pump the water twice to get it out of the river into our basins. The intake basically is our main supply to the plant, and it's basically pumped once. From there, they designed the treatment plant to gravity feed through the entire plant through the 3 different treatment trains or treatment process, which is a well-designed system. What you see here is our primary basins. Missouri River, as you all know, is affectionately known as the Mighty Mud. During the spring times, we'll see some high turbidities, and some people have said that during some times it's so turbid that you could walk across the water. That high clay, high silt content plays havoc on us, and we have to use special chemicals to drop the clays and silts out. So we'll use cationic polymer to attract the negatively charged clays and silts, and these primary basins are where that is captured. Because we like to make sure that as they leave the primary basin, say that the river is putting out or supplying 2,000, 3,000 NTUs, we like to make sure that leaving the basins is 50. Having that lower NTU will allow the chemicals to do its trick and try to get to any of the organisms that are in the water that might be detrimental to the public. You also see that we have we use a lot of lime in our treatment process. We use about 100 tons of lime on a daily basis to soften the water for the citizens of Kansas City. So, as you can see, we'll use one of these rail cars on a daily basis. This is another picture. We have 6 of these basins. Like I said, we have the opportunity to test out chemicals, whether it's polymer or which is another chemical that we use is ferric sulfate, which is a positively charged chemical. Depending on what the Missouri River throws at us, there's different geologic formations that get dumped into, or at least the tributaries that feed the Missouri River. Depending on where it comes from, we have different geology that provides different treatment options. Missouri River is basically a dam-fed river, and the last dam on the Missouri River is in Gavin's Point, which is basically what we hope that the Corps continues to provide enough so that way we don't have to use those auxiliary pumps. Once it goes through the pre-settling basin or pre-settling process, we then add chlorine for disinfection. We add ammonia as to turn it into monochloramines, and then we'll add lime. We use monochloramine as a disinfection because the city has over 3,000 miles of pipe underground that we push water through. And some of our water takes almost 5 days to get from the plant out to our customers. Having the monochloramines allows that the disinfection will stay in the water stable for a long period of time. If we were to feed free chlorine, the consumers would taste the chlorine. That's why the people of Kansas City can't taste the chlorine in our water, because the free chlorine in our water is below 0.5 parts per million. Total chlorine, we're over 1 part, which is by the state regulations we need to be at. But once we add the lime, then the lime attracts the minerals that make the water hard. As you can see in the picture behind me, you see the white areas. That's where we mix the lime in what we call flocculation. What we're trying to do is build big flock, essentially snowflakes for the layman's term. We want the snowflakes to get bigger and bigger, so as it exits out through these walls, you can see the faint hint of the pillows of flock that is moving from the flock zone into what we call a clarification zone. As you also can see that the water, that flock is very heavy, so it settles out very quickly, which is what we like to see. So the clean water, or the settled water, floats across the top of the clarification all the way to the south end, and for this being the north and that being the south. And in the middle, you'll see a large apparatus, which is rakes. Those capture the sludge that's produced, and it rakes it toward the center. With the amount of lime that we have to use, we have to get rid of our sediment somehow. We take that sediment, we send it back to the primary basins to help our chemical, or deter our chemical costs, and it helps the softening process in our primaries, and also helps mitigate as we return that material back to the Missouri River under our MPDS permit. The sludge that we that is captured, if we didn't have that rake arm, that basin would fill up within 24 hours and it would be locked full of sedimentation. So we're pumping that sludge back to the primaries on a daily basis. As the water continues, and this is a picture of what we do twice a year. It's called basin cleaning. And as you'll see, some of the equipment below, you'll see the rake arm down that is normally submerged. Maintenance staff has to do some preventive maintenance on these twice a year in order to keep the equipment functional. Like I said, if the rake arm failed, we'd get clogged up with lime and we'd have a problem. We've had some shafts break in our flock zone, and again, if we don't mix the chemicals up, we won't get good quality water. After the softening process, and the pH of the water at that point is about 11 and a half. Then we have to add carbon, CO2, carbon dioxide, and that's an acid that will lower the pH from the 11 to 10, which is what we give our consumers. In the recarb, what we call recarb basin, there is a process that, because we're in the agriculture belt, we sometimes have to deal with herbicides or pesticides that get our runoff from the farmers. And this is what we use to absorb the pesticide and herbicide. Again, we're all regulated by EPA and DNR for chemicals that is allowed in our water. And so by using carbon, we can absorb those chemicals that are health hazards to levels that are within acceptable limits. Besides the herbicides and pesticides, there are some times that we get involved with fuel spills. Barge on the river has a problem. A pipe line breaks up in Atchison, Kansas, and some oil spills on the river. We have to use carbon to absorb the petroleum spill. Sometimes we'll use the carbon to take care of some taste and odors. Now, every spring, after a nice dry winter, vegetation in the dry creek beds and dry dry rivers eventually get flushed into the Missouri River. And when that happens, the water gets a little tasty. So we'll add carbon at large quantities to absorb that tasty water. Now, we can't totally get rid of it, but we will mitigate it down to a little bit more palatable level. Once we've added the carbon dioxide, then we allow the water to settle again. The water takes approximately 4 hours to go through each of these basins. So water takes anywhere from 18 to 24 hours, depending on our flows, to go through this treatment process. It's all, again, a very extensive recipe that has been going on for longer than I've been at the water treatment plant, and it works. Once the water comes from the final basins, which is what we call stabilization, it goes into our filter gallery. As I said, we've got 36 individual filters that what I like to call polish the water. The water is drinkable in the final basin. It's just a little chunky. There's calcium carbonate that is suspended, but by passing it through our sand filters, it will grab that, keep it on the top, and then it filters out that material and whatever else might be in the water to the point that we put out the quality of water that is expected by our citizens. Now, EPA and DNR requires that this facility be below 0.3 NTUs for our consumers. Kansas City is working with American Water Works Association. They've got a program called Partnership for Safe Water, and we've been meeting the 0.1 NTU for the past 10 years. With the modifications that we've gotten accomplished through engineering and bond sales, our filter have become more efficient, and we've been able to meet the 0.1 on a very regular routine basis. And what that does for the consumers is it just means that the water's safer, a higher level of safety for the people that drink our water. The one nice things about the new filters is that in the old filters we had to use hoses to break the sand filter surface because it would get a layer of crust on the surface. So we had to use fire hoses to break that up. With what we have now, we have air that we induce in the bottoms. And what you see coming out of here is all the calcium carbonate that's captured on the surface of our sand. That's what's not in your water. That stays on the plant. But we use air and water to scour the sand to get it clean, so that way we can continue producing the clean water. We can run a filter over 5 days before we have to backwash a filter, and that's a huge savings. And with the upgrade that we've done with our filters, we've decreased our wastewater usage by cutting it in half. So again, we're doing things to improve our use of money, so we keep our costs down to the consumers. One of the things I like to brag about is these pumps that you see behind me. These pumps were actually manufactured in 1928. They're a workhorse. I would like to say it's a Cadillac, but Cadillac is no longer stigmatism of a superior car. You have to go to a Mercedes, BMW, Audi, Lamborghini if you want to go that route. But these are a very well-constructed pump. They'll last another 100, 200 years as long as we do the preventive maintenance. They were built to last. One of the things that bothers me about what we do these days, and as an engineer, the safety factors have decreased. Back in the 20s, their safety factor was larger, so it would last longer. But cost savings have to be made, and so if you want something this well designed, it's going to cost. But as long as we do the preventive maintenance on equipment like this, they will last. Now, these pumps behind me are pumps that pump across the river. We have 2 tunnels that provide water to the south. One was built in 1928, and the other one was built in 1990. And both of them go 300 feet below the Missouri River and come up on the other side, on the south side of the Missouri River, and then goes into two of our reservoirs that get pumped further south. These pumps here do about 55 to 65 million gallons a day, but they're only pushing about 15 to 20 psi. These pumps here are what we call vertical turbine pumps, and those supply the north. For those people that live up north, or a frame of reference is a Worlds of Fun tank. That's a Kansas City water tank. Those pumps pump to that area along with our Arrowhead tank and another pump station over near on the west side near Wacomas Lake. Those do 3 million gallons at anywhere from 150 to 180 psi. That's a lot of pressure to get up over the hill. Versus those horizontal split case pumps that only pump 15 psi to just get across the Missouri River. Now on the other side of the Missouri River, we have two pump stations that have similar sized pumps like that. Unfortunately, because of the pressure to get up over the bluff or move it further south toward the plaza, toward the zoo, those pumps do anywhere from 25 to 36 million gallons a day, and again they're pushing 160 to 150 psi. Large pumps, low flow, high pressure. As I was saying, we've got two tunnels that provide water to the south. The city has 17 pump stations. We have 3 pressure zones to the south. What that means is that water's pumped from the water treatment plant to these pump stations. There are reservoirs that hold the water for a short period of time, and then it pumps it further south. And then there's another, there's 2 other pump stations that have underground storage to store the water for use, and that's pumped into what we call a south booster. And then there's several pump stations in what we call the super booster. Now north there is just the direct and then the booster system. Worlds of Fun, past Worlds of Fun is what we consider the booster. The North Oak tank at 108th and North Oak, that's what we consider in the booster, and then KCI, of course, is in the booster system. Those pumps that you saw behind me, those are 1,000 horsepower pumps. The motors that you saw in those, and we have some larger motors that are 2,500 horsepower pumps. Those are large motors. Now the smallest motor we have pumping water is 20, very small, and they're doing about 100 gallons a minute. As I said, we've got 100 gallons a minute all the way up to 55,000 gallons a minute that we're pushing water. It's a lot of water to be pushed, but we do this because the citizens need it. We have 21 reservoirs. We have about 150 million gallons of water that is stored in our reservoirs for peak consumption, for fire flow, for storage in the event that something may happen that we need to do work at a location and we need to pump off the reservoir versus taking water off the system. Kansas City provides water besides the consumers. Within the Kansas City area, we have 33 wholesale customers. We have over 600,000 customers that we provide water to on a daily basis. So, wake up in the morning, take a shower, flush the toilets, brush your teeth, drink your coffee. The water in the Kansas City metro area comes from this facility, and my staff that works for me do a very tough task on a daily basis to make sure that the water is of the best quality we can. We live in the city, we drink the water, we work with each other. We have neighbors that we want to make sure that our water is the best that we can. We don't want to fail our consumers. This last slide is our SCADA system. How do we manage these 17 pump stations? Well, they're unstaffed. Through electronic technologies, we are watching the entire system on a computer. And that individual is sitting there 24 hours a day, turning on and off pumps, making sure the pressures are what they need to be for our consumers, as well as maintaining storage levels, whether it's an elevated storage tank or a ground reservoir. We want to make sure that we maintain pressures and storage capability for our consumers. And with that, if there's any questions, I know the Royals are playing tonight. Some of you all might want to watch the Royals. Hopefully they're going to win tonight. I got money on it, so I'm hoping that they do. If they don't, I'm going to be a little upset and a little down in the pockets, but you know, I'm hoping. We want a World Series win this year.